Gott fólk, velkomin á fyrirlestur í boði Náttúruverndarsamtaka Íslands og Hafrannsóknastofnunar súrnun sjávar. Við höfum fengið hingað frægan vísindamann frá Bretlandi sem heitir Turley. Ég hef séð hana og hitt á ráðstefnu Sameinuðu þjóðanna um loftslagsbreytingar, fyrst í París 2015, Marrakesh 2016 og síðan í Bonn í fyrra. Og svo sá ég að við erum að fá hana hingað til lands til að halda fyrirlestur þessi mál. Hún er mjög góð fyrirlesari, þekkir þessi mál mjög vel og áður en við bjóðum henni að halda sinn fyrirlestur ætti að bjóða Hrönn Egilsdóttur að kynna hvernig rannsóknir á súrnun sjávar hafa verið hér á Íslandi. Gjörðu svo vel, Hrönn. Takk.
Thank you for coming. On behalf of the Marine Institute, I will introduce ocean acidification and what's happening here in Iceland when it comes to that kind of research. Because the Institute is the main researcher when it comes to ocean acidification research, both in terms of the knowledge is mostly here today, but also the infrastructure to do this kind of research. You need to have very good infrastructure, and this is what the Institute has, although things could always be better. So the Marine Institute has actually been doing ocean acidification research as long as anyone, because the Institute started with 2 time series stations of CO2 in the surface water of Iceland in collaborations with other partners in the year 1983. This is the year I was born. It's quite long ago. So I had obviously nothing to do with it. But basically, the idea with this research was to investigate the flux of CO2 between the atmosphere and the ocean. At this time, the scientific community did not really think ocean acidification would become such a big problem as now we know it is. And a few years ago, they added another long-term station here. So the Institute has done an amazing job, actually, in providing this data, which has been used and cited extensively throughout the world. And provides this data into data banks where it's widely used for modeling, etc. In the year 1994, the Institute added a measurement of the seawater column. So now we see also, from that data, we know that the deep sea is also being acidified. And we know that the cold water north of Iceland is particularly the problem area. For example, here south of Iceland, or southwest of Iceland, sorry, in the Irming Sea, we see very clear surface ocean acidification in this time series. North of Iceland, we clearly also see surface ocean acidification. But here, we also see deep sea ocean acidification. At 1,700 meters depth, the ocean acidification rate is 4 times slower than at surface, because CO2 takes obviously time to get into the water, into the deep water. But it's happening, and this is a particular concern, especially because the calcium carbonate saturation states, basically relates to how calcifying species behave. Calcifying species form calcium carbonates, and what we're doing is we're making it harder for them to do that, because we're taking carbonate out of the system via ocean acidification. And we see that in the Iceland Sea, the calcium carbonate saturation states are decreasing quite rapidly as well, and are already low because the water temperature is low. There have been other works done by the Institute throughout the years, including underway PCO2 monitoring that also has been put into database, and buoys that have been put out in the water in cooperation with NOAA. So just to give you an example of what this data is telling us, this is a time series for pH in the Iceland Sea, north of Iceland. And it's not very often in work on natural variability that you have such clear trends, but really you cannot say that ocean acidification is not happening here. It clearly is, and these time series stations, which were critical in waking up the scientific community in the beginning, because we didn't really see any publications on ocean acidification until just before the year 2000. So it wasn't until here that people realized, here's the year 2000, that people in the scientific community and later the public and policymakers realized that this was such a big problem. So these time series stations were critical in telling us that. So what else have we been doing? I did my PhD thesis here and at the University of Iceland. And basically looking at the data from the Institute throughout the ages, I decided that we needed to know who would be affected. And so it's really a hard thing to do. How can we monitor the effect of such big changes, especially because the vulnerable marine species are often the ones we care less about in the economy, like bivalves and gastropods. But we have quite amazing data actually from 1991 to 2004 on the distribution of bivalves and gastropods. So we did some studies on the biodiversity, really to tell us the background data of who is there. This is the first step in knowing how things are going to change, is how has it been, who's there, what species are there. We really didn't know that a few years ago. What we also did in this project, because Solveig Rósa Ólafsdóttir and colleagues were doing already measurements of the system in coastal fjords, especially Breiðafjörður. They added a measurement of CO2, an inorganic carbon system. And these are 5 stations we had in this project to just know the seasonal variability. Because we know that the ocean acidification is not happening slowly and that there's no variability in the system. There's always variability in all systems. And this is important. We need to know what the variability is so we can know how things will change in the future and so we can know how species will react to these changes. So we did some measurements of inorganic carbons, PCO2, omega aragonite, we calculated, which is basically the saturation state for calcium carbonate, a calcium carbonate type that is formed by bivalves, for example, and the pH. So now we have an idea what the seasonal variability in the coastal system in Breiðafjörður is. This is extremely important information for any studies on the biological effect of ocean acidification here. But in the future, the marine and freshwater, it should be MFRI, so the Marine and Freshwater Research Institute aims to do several more things than we have already been doing. For example, measure in more detail and describe the natural variability in more systems, in the carbon system, in different habitats, and also add some monitoring of vulnerable benthic species that could be our canary in a coal mine. But this work sadly remains to be funded yet, but hopefully we will see some change in the future. So, Carol, thank you.
Thank you for that truly marvellous talk. One thing I've realised is that I've learnt over the last few days is Icelandic people are very modest, and this includes the scientists. This research, this 30-year-long observations of ocean acidification around your coast is remarkable, and it's beaten by none, and yet boasted by few. So really, you must keep this up, and it's such a hugely important part of the whole global picture, because Iceland really is on the barrier, on the canary in the coal mine, which is a wonderful analogy. I've been asked to give a global perspective, which I shall now go back to. It's not mine, I turned mine off, I think. So what is ocean acidification due to? It's due to mainly CO2 emissions from the burning of fossil fuel. Now, around 47% of that stays in the atmosphere, and this is what we know contributes to global warming and climate change. The other proportion is taken up more or less equally by the land and by the ocean. And what you can see here is the atmospheric CO2 increasing and the ocean pH decreasing. And you saw the long-term observations showing the decrease in pH of the Icelandic coast. This is what's happening all around the world, in tropics and different oceans, but it's happening faster in the cold waters of Iceland. So the chemistry is really simple. It's basic school child chemistry. There's no debate over that. CO2 plus water equals carbonic acid. And this is what we're calling ocean acidification. So the ocean is buffering climate change by taking up a great proportion of the CO2. But it's not all about pH. And a pH is the measure of hydrogen ions. It's about more than that. It's about a whole change to the carbonate system. And importantly, it affects the carbonate concentration. It decreases that. And this is a real issue for calcifying organisms that are very common in the marine environment. And also, calcified structures will actually dissolve at a certain level of saturation, of concentration of the carbonate ions. Now, if we look back in time, so we're going backwards in time this way, and you can see the kind of change that we will undergo in the next decades is actually greater than what has been seen for millions and millions of years. So what we're doing as a human species is actually amazing. That's one way of saying it. And this is a model by Jim Orr, and it's the worst case scenario. And this shows the change in the saturation state of aragonite. Aragonite's really important. It's used in a lot of marine organisms to produce their shells and skeletons. For example, deep water corals use aragonite. Pteropods, little sea butterflies, use aragonite to make their shells. And as you can see, the whole global ocean is impacted. And that saturation state is decreasing down across the whole global ocean. And it might have come to your attention that the Arctic Ocean and the Northeast Atlantic will become undersaturated first. And that's closely followed by the Southern Ocean down here. And so you really are this canary in the coal mine. And that's why your observations are so important. And there was mention about variability. And as you move towards the coasts, the variability of this ocean chemistry changes. You can see in the North Sea, these are observations, and you can see at the surface, the ocean pH is much higher than on the seabed. So it's really important to understand what's happening below the sea level. And here in the Pacific, you can see how it changes with depth as well, from high to very low. So there's a lot of spatial variability, and that's a real challenge now for scientists to understand. And we have to do that by observations and monitoring. So we're seeing the impacts on the chemistry. That's certain, that's already happening, and it will continue to happen as we put more CO2 in the atmosphere. That's inevitable. And there'll be impacts on marine organisms. We're seeing those already. And that will affect food webs, biodiversity, and community processes within that biological community. But also it will affect biogeochemical processes, which will feed back to climate as well. Now, this is far more unknown, and it's a major question for the future. And of course, changes in our ecosystems will affect our fisheries and coastal protection. Now, in the last 10 years or so, there have been a substantial investment in ocean acidification, trying to look at the impacts on different organisms. And it's been a remarkable undertaking by scientists all around the world. And this is kind of all that data pulled together in a meta-analysis, and surprise, surprise, they find out that calcifying organisms seem to be more vulnerable than non-calcifying ones, with corals, shellfish like mollusks, calcifying algae, which are really important in terms of binding reef systems together, and then other calcifying organisms as well. Whereas fleshy algae and some diatoms might actually do well in a high CO2 ocean. But any shift, be it positive or negative, has ramifications for the ecosystem. So that whole balance is shifted. Now, just to go to warmer tropics than here. There's this fantastic experiment that was carried out in the Great Barrier Reef. And what they did is they took a whole reef system and changed the chemistry, the carbonate chemistry, back to what it was 200 years ago, pre-industrial times, and said, okay, what's your calcification rate now? And they found that it was around 7% higher than it is today. And this indicated that ocean acidification is already impacting coral reef ecosystems, the calcification. And that's supported by long-term monitoring of calcification of coral reefs as well. And these sorts of experiments are really, really important for us to know what's happening now, because we keep thinking that today is normal. In fact, today's halfway along the process of acidification. Other areas that really give us an insight into a future high CO2 ocean are natural carbon dioxide seeps. This is where CO2 seeps through the seabed into the surrounding seawater. And this is one of the first ones that was studied in the Mediterranean. And you can see at today's pH of around 8.1, a really great biodiversity, lots of calcifiers, you know, healthy looking ecosystem. And then towards these vents, so that's away from the vent, as you move towards the vent, you actually see an enormous change in the biodiversity and an increase in algae, fleshy algae, and nuisance species. So, and this massive change in biodiversity. So these are like a window into a future ocean, into a future high CO2 ocean. And there have been other studies in coral reef systems as well. I wonder, are there any CO2 vents around Iceland? Could be. Yes? Wow. I feel a project coming on. Well, they really can be very, very good study sites, fantastic laboratories. And of course, cold water corals are hugely important around both UK shores and the shores around Iceland. And we've been studying them in the UK as part of the UK Ocean Acidification Research Programme. And by combining our work and looking at models, these are models of aragonite saturation, that's the calcium carbonate mineral that cold water corals use to make their skeletons. You can see that at present, anything that is below 1, that is in the orange and red area, is basically corrosive to cold water coral ecosystems. And that's because cold water corals grow on the bones of their ancestors. So it's a kind of a rubble mound that builds up, but that rubble mound is a wonderful ecosystem and an important nursery ground. So as you can see, coming down here, business as usual. This is if we keep on burning fossil fuels at the same rate, you can see that most of the area is corrosive to the cold water corals. And even living cold water corals that have that protective membrane, we're finding in our research in the UK that they're more brittle, so they won't be as strong. And then RCP 2.6 at 2100 is that 1.5, that Paris Agreement of 1.5. And you can see even at that, at 1.5, there's still an issue in terms of ocean acidification, but it's far better than the higher emissions. So I don't know, I think Iceland might be particularly vulnerable to ocean acidification. If you look at the Paris world, there are areas that are still healthy in terms of aragonite saturation, but business as usual, it's not looking good for anyone. And it's not looking good for the North Sea as well, so don't feel isolated in any way. Now, the impacts on the biology are quite hard to determine because marine organisms have all these different parts to their life cycle. And so you need to look at all of these. And scientists have shown that the adults, whilst the adults may not be as vulnerable to ocean acidification as the youngsters and the juveniles and the embryos. And of course that affects the population fitness. So the whole study of impacts is far more complicated. And then the organisms in the ocean, like us, have to regulate their internal pH. So each of us spends a lot of our energy maintaining our internal pH in our blood and so on, and getting rid of these hydrogen ions. And normal organisms in the ocean do that. This is how they spend their energy that they get from eating their food. So, a good portion on maintenance, some on reproduction, and quite a bit on growth. Now, if you stress an organism, they have to spend more on the maintenance and less on the reproduction and growth. So again, this will impact their long-term fitness. Now, these little mollusks, tiny little marine snails, are really important in the marine system. And they're just about visible to the naked eye, and some people call them the potato chips of the sea because they're so numerous. And they're actually dissolving off the coast of California because of the upwelling there, plus the acidification that's going on there, and in the Southern Ocean. And I think there's some studies about what's happening in the Arctic as well, but we can discuss that later. And they're a hugely important part of the food chain. You can see the Pacific salmon, nearly 50% of the gut content of Pacific salmon are these potato chips, and they're very, very important in the Arctic and Northeast Atlantic as well. Now, economic impacts are already happening, and the first ones happened off the coast of the United States, and these were the oyster hatcheries, and for several years they had basically 80% mortality of the hatcheries, and they didn't know what, they thought it might be a virus or a pollutant or something, and eventually they were able to work with NOAA scientists and actually find out that it was due to the upwelling of high CO2 waters, plus the acidification that was happening from the atmosphere. Now, they've been able to adapt to it by monitoring, by seeing this upwelling coming and then changing their system, turning their system on. So they observe for their oyster hatchery. Now, other hatcheries moved to Hawaii in order to save a bit more time, but they all know that this is a temporary solution. And these are fishermen that are actually go and talk at the United Nations and tell their story because they believe it's really important that the world is aware of this ocean acidification issue. This is I had wonderful shrimp last night. As you know, the Swedes also love shrimp, and Sam DuPont, who works in Sweden, got a very well-known chef in Sweden to cook shrimp, some grown at high CO2 and some grown at normal CO2, and then got a blind sampling done by members of the public, and they preferred low CO2 shrimp. So they're finding that things like flavor and fatty acids and so on are being impacted by ocean acidification. So what are scientists doing about it? We know about this. We're worried about it. There are very few long-term observations. And so what we're doing about it, in 2012, we formed the Global Ocean Acidification Observing Network. And Iceland's part of that, which is fantastic. And this is really to document the status and the progress of ocean acidification so that we can actually inform models, so that we can inform policymakers, so that we can look to the future, project the future. And it's kind of like an early warning system that we want to build. What we're also doing is trying to build capacity around the world, because there are many, many areas of the ocean that don't have ocean acidification observations. And so those people with expertise in measuring it are sort of building capacity and training other countries in how to do it. So I have to say that it's grown over the last 6 years to over 400 scientists from 77 countries, and it's growing every day. And just very recently, to make all of this work, we've decided to have hubs. So there's a Latin American hub. So basically you build hubs of scientists so that they could inform their own groups better. And the Northeast Atlantic hub, which is a very, very important one, is being coordinated by my institute, and that's really to promote ocean acidification in the European and North Atlantic context. And we've managed to get funding from our government for 1 year in the first place to do that. We hope to have a workshop where we want to bring all the experts together. So invitation there, do come in March, probably next year. And we will have a website. It's really to build the best practices for measuring ocean acidification and communicating that. And we're looking for national champions. So that you can really input into this. This is for scientists, by scientists, with the link really to inform policy. So, you know, potentially in the future, the next or one of these meetings could be here in Reykjavik, you know, really to spread the knowledge and the load. Now, ocean acidification isn't happening on its own. The ocean is also absorbing around 93% of the heat from ocean warming. And that's warming the ocean. It's when you warm a liquid, you lose gas, but also you form a top, you stratify the top, so there's less communication and transfer of gases from the atmosphere into the ocean. So this is what we call deoxygenation. So the ocean is losing oxygen too. And of course, ocean circulation and mixing are affected, and this could have huge impacts in terms of ocean circulation, but also the strength of hurricanes, and, as we've heard. And it's also receiving all the water from melting ice, plus the thermal expansion of the ocean due to its warming is resulting in sea level rise. So I give to you, the ocean is truly at the front line of climate change, with multiple stresses, with the first 4 of these actually really directly related to the climate change negotiations. So that's the United Nations Framework Convention on Climate Change. And that's why we really need the ocean and its ecosystems as part of that debate. It's so important. And I'll tell you why. So these are different scenarios. This is where we are now. Global mean averages, all of these, nothing to do with Iceland, but you will be more extreme. So here we've got the air surface temperature, global mean, has increased by just over 1. Sea surface temperature by 0.8, and ocean pH has decreased by 0.1. Now that doesn't sound a lot, but it's around 30% decrease increase in acidity. Now the 1.5 warming, which is RCP 2.6, that's average warming. There's a report came out on it today. This results in 1.1 sea surface temperature rise and a 0.15 decrease in pH. I shall jump to here because the 4.2, if we do nothing, the average air temperature globally will be 4.2, with 3, the sea surface temperature, there'll be an average of 3 degree rise, and pH will fall by 0.4, which is around 150% decrease in pH, which is just amazing. NDCs. NDCs are what different nations have voluntarily contributed to decrease in terms of their CO2 emissions. And if you add all these up, you can see that the current air temperatures will be around 3 degrees, sea temperature will be somewhere between 2 and 2.6, and there'll still be a substantial decrease in ocean pH. And the Paris world, which is of 1.5 warming, there'll still be an increase of over 1 degree warming of sea surface temperature and a 0.15 decrease in pH. So what this shows is our current NDCs offers of CO2 reductions following the Paris Agreement are not enough to have substantial impacts on the marine environment. And this is a paper we brought out in 2005, just before the Paris Agreement. This is business as usual. The dark reds and oranges show the strength of risk to key marine habitats and goods and services. And you can see that nearly every single one is high or very high. This is the low CO2 scenario, which is equivalent to the Paris Agreement of 1.5. And you can see that once you decrease that risk, there is still some ecosystems that are critical for that. But also the management options decline with higher CO2. So what's this actually mean? Say for warm water corals, business as usual, the risk is very high. I think the report that came out today shows that business as usual, you'll be lucky if 10% of the corals survive. The current NDCs, you reduce it a little bit, but not a lot. Paris goal, you reduce it a lot, but it's still a very high risk to tropical corals. And I think the report today said that around 30% may survive. In terms of finfish, again, you can see that business as usual is very high. This is in low latitude fisheries. NDC, some improvement. Paris Agreement actually does make quite a substantial difference. And then there was a paper out last week which was looking at the sensitivity of key ecosystems and their services to these climate-related drivers. And they particularly looked at warming and acidification, as well as sea level rise, but I'm focusing on these two. And you can see that Arctic biota, there's a very high sensitivity to warming and a medium, moderate sensitivity to ocean acidification. And this is also reflected in fin fisheries. So this is showing that the chemistry and the physics is really, really linked to the ecosystems, and those ecosystems are linked to the services, the goods and services that the oceans provide. So the most vulnerable societies will be coastal communities, directly relying on marine productivity or coastal protection. And many of these will be highly vulnerable. Now, it might be small island developing states that their main source of protein and income are fisheries, and they don't have much ability to adapt and find another income. It could be a very well-developed country like Iceland, where fisheries is a hugely important part of the economy. So my conclusions are that we need wider monitoring of ocean acidification, both the chemical changes and the biological effects, that current commitments from nations to reduce their CO2s are simply not enough to avoid the risk of impact to ocean ecosystems and the goods and services they provide us all, and that we need to build on them urgently, and we need more ambitious CO2 emissions reduction, which kind of basically sums up the 1.5 degree report in some way. Now, I just want to spend a couple of minutes on what the UK is doing. Is UK really sees that the changing Arctic Ocean is a hugely important area for research, and we're investing a huge amount into looking at the impact of that change in the physical and the chemical environment. So ocean acidification is part of that, but so are the other stresses. And we funded 4 large £2 million programs last year. And this year we joined with the German government in a collaboration with 12 new projects of £800,000 each to really look at the impact of that. If you look at, there's a huge number of scientists involved and institutions, and we collaborate with other countries, including Iceland, and very much we are collaborating with policymakers as the policymakers really need to know the science very early on. I'm involved in one of these projects which is called Petra, and that's looking at the biogeochemical aspects. What are the feedbacks of this changing environment to the production of other climate relevant gases? Because that is truly an unknown at the moment. Many thanks for listening to me. If there are any policymakers here, we have a little summary, and I've got some copies here, but it's called Oceans of Impact, and we produced this in order to really advise the policymakers of what's happening in the oceans, and we try and put it in accessible wording for them to digest. And those are my science conclusions, which I'll leave up for a minute, but I just rushed to the website this morning and I downloaded a couple of bits that mentioned acidification. It's in there. Do read the report. Read the details in the report, not just the summary for policymaker. And I think our future on this planet as a global society really depends on the next 10 years of action. It says we have got 10 to 12 years to actually start making changes. So let's go to it. Thank you.
Thank you very much.
Thank you.
Yeah, I can invite people to ask questions. Or any. It's quite a depressing subject, but can I maybe ask a question?
You may.
Because I'm curious, I work in ocean acidification, but it's really hard to understand how we can put this information in good context for the policymakers and the stakeholders. How do you feel like, for example, the stakeholders in the United Kingdom, are they responding to this message? Are they listening to what is being said about ocean acidification?
Well,
the fisheries themselves?
the whole world is, in a sense, because following the Rio +20 convention on the Sustainable Development Goals that were developed from Rio +20, SDG 14 is life below the ocean. SDG 14.3 is specifically on ocean acidification. So for nations to deliver the SDGs, they really need to look at 14.3. So acidification, and it's all about collaboration, it's all about science, and that's what we need. And yes, our government funded jointly with our research council the UK Ocean Acidification Research Programme, which was over £12 million over 5 years, and has funded since then. And that was a multidisciplinary programme, including the geology, the biology, the modelling, the physics, the whole thing. Unfortunately, it was 5 years, and so we're now pressing our government to actually increase its monitoring of acidification, because we've got a station off Plymouth and we've got one off Scotland, but they're nowhere as long as your ones. You know, yours are twice as long as ours. So, but what we want to do is you know, make sure those on a good funding for the future, because that's essential, because that informs our modelers. We have ecosystem modelers that develop ecosystems that include ocean acidification in shallow waters as well, not just deep waters. So it takes into account all that variability, and so that we can project what's happening in the future. And our governments are very interested in that.
One question in the back.
Are current NDCs being met by at least most countries? The NDCs,
Yeah,
are they being met right now?
I don't know. Because I think one of the issues, correct me if I'm wrong, is actually having a means of verifying NDCs. So that, I mean, that is a big science issue in its own right, is the verification. So
what would be the point to be building on them if we don't even know if they're being met right now? And what's like, because I was thinking about which countries would be the ones that are not currently meeting them, and how we could help them meeting them first and then building on them, because it feels like it's like a never-ending wheel. If you're not even meeting the current NDCs and you're pressuring this maybe a third world country to no, you have to go even further than that. It's just a thought.
well, I wouldn't be so negative, you know, by saying what's the point if we don't know. The point is, and we do know it, is that we have to, every country has to increase its CO2 emissions reduction. Yeah, that's known, that's the knowledge. So I'm reversing your negative into a positive.
So we have two more questions. Halda Björnsson, who is at the Meteorological Institute.
I have a question regarding my field of time is more on greenhouse effect and global warming. You always have these people who come up with sort of schemes that range from being mildly insane to being totally so about sort of planetary engineering. You know,
Geoengineering, yeah.
put something into space to take off the sunlight. Are there any such plans for large-scale engineering? There's nothing really to do except reduce emissions, is that?
Well, do read the 1.5 report. I haven't had a chance to read it, but they do go into what can we do about it. And because achieving 1.5 means we have to remove CO2 from the atmosphere. So that's essential. And there are two ways of doing that, is plants, which are very effective at removing CO2, and another way is geological sequestration, so carbon capture and geological sequestration. But it does go into all of that. It's worthwhile reading. And
yeah, but for ocean acidification, my point was simply that there's no chemical trick that you can do.
yes, you can add alkalinity, but that's totally unproven. And a lot of these technologies are totally unproven. And so that's why we actually need research into these, because people will be turning around and saying, well, why don't we throw some alkalinity into the water and it'll all be okay? But what's the effect of increasing the pH by a huge amount before it's dispersed, you know, and how expensive is that? How much CO2 do you have to do to mix it in, you know, to create this? So we actually need to do research into some of these geoengineering solutions, but mostly it's about removal, not about solar. Solar reflecting the sun out won't help acidification at all. That's for sure.
So I think we'll give two more questions.
Oh, do
sorry.
we have one here?
Oh, sorry. Yeah.
One question here. Thank you very much, Carl.
Turley. I was so lucky to my first meetings in the Paris when we're actually negotiating the Paris Agreement. I managed to listen to one of your talks there, which then explained to me as a layman totally the sort of the framework of what is happening with the oceans. And what I realized also there that we haven't really been discussing as policymakers the implications of the oceans within the UNFCCC framework. And I think what maybe I saw it was kind of maybe lacking in that was to bridge that gap between all your scientists who are doing this important work and the policymakers. So I would like to ask you now, I mean, I know that the oceans has been incorporated a little bit better into the UNFCCC, but do you think we can do more there to incorporate it as a platform within the UNFCCC where the action is actually taking place in decision making?
Yes, I truly hope so. And following Paris was Marrakesh, and the oceans. The UN included the ocean into its process as the ocean action event. So it had a whole day on the oceans, which again was a breakthrough. And Paris included the word ocean and its ecosystems in its preamble, which, believe it or not, was a major breakthrough. Those 3 words were, you know, I mean, crazy, I know, but they got in there, which is fantastic. The Paris also asked for a special report on the ocean, and that's being written at the moment. I'm part of that. That will come out next year, and that's on the ocean and cryosphere. So that will be an important report. So that will be out in time for the next COP next year, not this year. 1.5 has come out for this year, so next year. And I think the whole thing about ocean acidification and the ocean is that it appeals to nations that wouldn't be interested in climate change. You know, so it brings added arguments to the table. And really, the ocean is part of the planet. And the UNFCCC is all about changes to the biosphere and the geosphere and the hydrosphere. And so it really falls under the auspices of the UNFCCC. And, you know, if you've got any ideas of how we can get more in. But in Bonn, the last one, Fiji had the presidency of the COP, and they pushed the ocean pathway, which was they were trying to find an ocean pathway to really get the ocean into the negotiations.
I'm going to have 2 more questions because we're running a bit out of time. But Sigurður Gislason was a professor at geochemistry at the University of Iceland.
Okay, thank you very much for an excellent talk. And I'm wondering if you were alluding to Iceland in your last comment, you know, because Iceland had high hopes in climate change, with the warmer climate. And then when we started talking about ocean acidification, then we get too serious because we might lose our fisheries.
Yeah, I've got friends and family too that say, God, wouldn't it be nice if Britain was 2 degrees warmer? But it doesn't work like that. We're seeing huge changes in our weather and our climate. And you've got to remember we've adapted to the climate that we have. No doubt we can adapt to a future climate, but at great expense. And you know, adapting to sea level rise is something that is just going to be extraordinarily difficult for not only my nation, but also many peoples around the world. So I think you've got that interesting bit is that your oceans are going to warm, as are ours. We're seeing an influx of invasive species. We're seeing loss of fish that we used to have. And so this, you know, things are not predictable. Things are changing because ecosystems are changing. Fish are migrating.
The irony of all of this is that if we didn't have ocean as, when if we didn't have dissolution of carbonates in the ocean,
Yeah,
then, there will be more CO2 in the atmosphere.
that's right.
So if you look at long-term prediction, that in the first peak after 250 years, when we are at the peak of emission, if we do business as usual, then when we start is dissolving, keeping in the ocean, and then when the carbon starts to dissolve, when dissolving the corals, then that brings the CO2 down. So that is kind of a
Yep.
defense mechanism for the ultimate horror.
Yep. In a sense, the majority of the CO2 will end up in the ocean. But it's the ocean processes, the Earth system processes, and the CO2 reaction with the sediments that will ultimately buffer the CO2. But this will take 70 to 100,000 years. We don't have time to sit down and wait. We evolved, modern man walked out of Africa 70,000 years ago. And within 200 years, 300 years, we've changed the planet to...
I would like to take this a little further. It will take us 500,000 to a million years, because the eventual push to pre-industrial CO2 in the atmosphere will be done by weathering of silicates
Yes,
on
yes.
the surface.
Yeah.
So we're talking about 500,000 years to million years.
Yeah, but what we've done in 300 years, 200, 300 years, is made the Earth system change so much that it will take that long. So it's amazing. It's what a species. But we are clever. We can do this. It's exciting. It really is challenging.
Yeah, I think my question has been partially answered, I think, right now, because I wanted to ask about the permanence of changes. Because we know with the warming that will, because of the lag, it will continue even if we dropped all emissions today. How would ocean acidification be affected? Are we now committed to a certain scenario, and how permanent is that going to be?
We are committed over the next several decades, but the more CO2 we put up into the atmosphere over the, from now to in the following decades, the worse it will be. So literally, if we start now, we can do something, and there is a lag in the system, so that the CO2 that's up there will have an impact on acidification as well. And so that's why we need removal. If you read the report, it's really interesting, is that, it'll take us this long to get over the peak, and then we need to develop removal systems in order to prevent the worst part of that, because there's this lag.
Well, my question more directly is, how permanent is the change in the acidification of the ocean? Will that be in some way reversed if we stop emissions, or will it be permanent for many centuries?
It will.
Thousands?
It depends what we do. If we stop CO2 emissions now, we will stop it going into the atmosphere and stop a lot of it getting into the ocean. Some still will go into the ocean. And then that will take a long time to get rid of. So the best thing is to stop it going in there in the first place.
But we're talking a time scale of hundreds of thousands of years.
Yes. Yeah. So, act now.
Thank you very much. I think
Okay,
we're running
thank
out of
you.
time.